speed is the,
Absolute value of velocity.
Oh, that one's distance.
was that's what, okay, but this is asking for distance.
Yeah.
Okay.
And then you get
All right, so let me go ahead and explain this to you. If you needed the length of a curve from A to B, I don't know if you remember when I taught you it, I started out with somebody in the room, I can't remember who it was, I think maybe it was Steffi, was like, maybe we could find the distance between 2 points and add up all those little distances, okay? And so you learn this formula that I started out with like this. The distance formula is x minus x squared and y minus y squared. Do y'all remember that?
Yeah.
Okay. And then we wanted to add it up from A to B. And what I did I said, remember this. I don't know if you remember that I even said that, but I said, remember this. That's going to be important later on, okay? But for our purposes that I needed you to do it a few weeks ago, I divided everything by dx squared, and I can't just throw this in without balancing it out. And what's the square root of dx squared is dx. So do you see I virtually multiplied by 1 there?
Mm-hmm.
All right, so I'm just redeveloping the arc length formula for you, or distance of a curve, length of a curve.
Mm-hmm.
All right, so that became the integral from A to B of the square root. If I put dx squared over dx squared, I got 1. And what did I call dy over dx squared? The derivative squared?
Mm-hmm.
All right, that's something that you should know that I've taught you. That's the length of a curve formula, right? That's if you've got it in terms of y in terms of x. Is everybody okay with that?
Mm-hmm.
All right. What we have right now, though, on number 5 is this. We have a parametric set of parametric equations, and so we could stop at our distance formula pretty much. Dx squared plus dy squared. Back when I first taught it to you, the length of a curve, and this is something traveling along a curve. I really wanted to get it in terms of a derivative. That's why I divided both by dx. All right? I wanted dy over dx. Right now I don't care though because x and y are separate components. I have an x component and a y component. So these are moving at a certain speed. So really we have a dx dt and we have a dy dt. So I'm going to divide it by dt squared, but in order to balance that out, I'm going to also multiply by dt. And so when I'm doing parametric form and I want to know the length of the curve, I can just leave them separate. I can take the derivative of x with respect to t squared. I can take the derivative of y with respect to t squared and throw it under the square root. And it'll add up all those little bits for me. And I think that setup's pretty evident now on number 5, which we'll do this again today, okay, in class. I just went ahead and when I was looking through what you were sort of able to do, I wanted you to try that one, but that would have been a new thing to learn there, okay. Now, Lola, what you said, this is very kin, also, it's ironically kind of kin to speed, because you've got some sort of dx dt and dy dt here. These are velocities. I'll get into that later.
Well, can we just finish the problem?
Yeah. What was x?
Sine t cubed. Or sine of t cubed.
All right, like this, x is the sine of t cubed.
Yeah.
And what is y?
E to the 5t.
E to the 5t. Good practice in taking derivatives without our calculator. Make sure you use the chain rule. All right, so now why is this dx dt? Isn't this derivative of x with respect to t? We're going to look at that a lot today. The derivative of sine of t cubed is cosine of t cubed. And then the derivative of t cubed is 3t squared. And then I need dy dt. Dy dt, the derivative of an exponential function is you always copy it down. Then technically you take ln of the base, but that's just ln e, which is 1. And then the derivative of the exponent, which is 5. And so I'm not really sure how it's written on your paper, but in order to find the arc length from where to where did they say to go?
0 to
0 to
pi.
pi.
0 to pi. I would go square root of dx dt squared plus dy dt squared dt. That'll give me the length of a curve. And so what you've learned is if you want the length of a curve normally, when you have y in terms of x, you say the square root of 1 plus the derivative squared. If you have it in parametric mode, though, it's really just a good old distance formula. X minus x, which is dx, y minus y, which is dy. So dx dt, so this is going to be 3t squared cosine t cubed. And this is going to be 5e to the 5t. And then did they go ahead and square it, or did they
Yeah.
just?
Squared it.
So everybody okay on that one? On the
Yeah, I
answer
just
choice?
grabbed the square.
All right, another question. Let's do one more today. Mark them off as we do them if you understand it. If you don't understand it, you can leave a question mark there and we'll try again another day. All right?
22.
All right, this is 22. All right.
Oh, this one was funny.
All right, let me see 22.
We had to do.
The table above gives the values of f. I better write it down so we can refer to it. You have f of x, f prime of x, g of x, and g prime of x. All right, so at 0, you get 2, 6, negative 4, 2. And at 1, you get 4, negative 3, 3, negative 1. Oh yeah, this one's interesting. So you have the integral from 0 to 1 of f prime of x, g of x equal 5. And they want you to somehow be able to figure out the integral from 0 to 1 of f of x, g prime of x. Like, what does that equal? Now, it looks like Joyce thought correctly. One idea is maybe the product, the integration by parts might give you that. I don't remember how I did this one. Let me
If
think.
you do integration by parts, you have to start with
Like, of f of x, g, or.
This is
Just
what it
like
calls to
integration.
mind. To me, it looks like so much like the product rule, which is really kind of like integration by parts is like an inverse product rule.
If you do the integration by parts of the second one, I don't know why, but I started with the first one and it didn't help. But if you do the second one, you
Uh-huh.
can actually find stuff to plug in.
Okay.
Into the.
Well, let's do that then. And then I'll maybe talk a little bit about where I was going
You
to
have
head
to
with
start
it.
with the second one.
Yeah.
Because
Yeah,
the second one is
I-
what you're talking about.
It just
Right,
threw me
I just
off.
did
It
this.
was like,
I did
why
the
did
first
they
one
give
because
us the
I'm stupid.
first part? Well, because then you use the first
Because
part.
you use the first
Oh.
part and the second part.
But I thought, like, okay, I'll find out what each of these equals in the first one. I was like predicting that was what they were gonna make us do, but.
Oh, and then that was
Yeah.
This won't scroll down. That's so weird.
Or maybe you lifted the page a little bit. Yeah, if you pull up the like actual notebook.
the whole thing.
No, like yeah.
Thank you.
There you go.
Okay. Let's see, Grace, did you let u be
F of x.
f of x? So if I let u be f of x, then du is f prime of x dx. And then dv is the rest of it, which is g prime of x, and I guess there was a dx back there I didn't copy down and I should have. And that'll give me v is equal to g of x. Is that what you got so far?
Yeah.
All right, so then when you put it together, you have u, v. This is so interesting as opposed to the way I was thinking about it. Minus the integral of f prime of x gx dx. So you have uv like minus the integral of v du. I don't know how long it took you to react that way, but a lot of times we need a reaction like that, okay? And then you knew this one was 5, right?
Yeah.
So you have f of x, g of x, minus 5
And then you have
equals
to go
what?
0 to
From
1.
0 to 1.
F
zero
of
to
x,
1.
g of x from 0 to 1.
Okay.
And then you use the chart.
Oh, this was all from 0 to 1.
Yeah.
So I have,
Oh, that's okay. Got it.
Isn't it
Equal to integral of g prime of x of x dx.
sorry, I'm having to think about this as I go because I didn't work it this way. Let's see, when you do integration by parts, so once you have an integrator, you're saying you do this?
Yeah, 0 to 1.
So 0 to 1.
But 5 is already 0, isn't it?
So I guess it's not going to be affected, is it?
No, not the 5.
That's why it confused. Yeah. that's why it confused
Is it going to be different if I do it here?
Yeah, it would be because you'd have minus 5 twice.
Yeah. We need that in there, I think. Because the integral of this one from 0 to 1, did they give you that whole thing?
Yeah.
Okay, it's 5. All right,
Yeah,
so
then
then
seven
you
is
got
minus
f of 1, g of 1, minus f of 0, g of 0. And whatever number you get there, you would subtract 5 from, and it gives you your answer just.
I just didn't think to do it from 1 to 0 once you got the UV.
Yeah.
Yeah.
Yeah, that confused me a couple times on this test when I was supposed to do from 0 from like.
Sometimes I'll go off to the side and do a little one, kind of, so many times you do integration by parts, you don't have limits of integration. And so
Yeah.
sometimes it's hard to think about what do you do when I do have limits of integration.
Yeah, exactly. That was one of many.
Let me talk a little bit. I think this is how I worked it the first time. I may have only worked this problem once in my life, but I think what I saw when I did this, let me see it again, Joyce. When I saw the integral from 0 to 1 of f prime of x, g of x dx is equal to 5. And I wanted the integral from 0 to 1 of f of x, g prime of x dx. Okay, I think what I thought of is if I have f of x, it's interesting how this works out, g of x, and I take the derivative of it, I would get f of x, g prime of x, plus f prime of x, g of x, right? Product rule. I would have first times derivative of the second plus second times derivative of the first, if I wrote that a little bit better in front there. So then, I'm trying to think what I did from there. I know I've worked it that way before.
Don't they give you the values already for f of x and g prime of x?
Yeah, I think
So you could have just plugged those values in?
No,
At
they
some
didn't give
point,
us exact values for those.
yeah, at some point I integrate it though, because I've got to get the 0 to 1 in there. I can't remember what I did here. I think that I did this. I think I integrated both sides. And if I integrate derivative, that gives me f of x, g of x. But that's from 0 to 1. Is equal to this integral. They gave me one of these. Which one did they give me?
Oh, yeah. They gave you
The second one.
second one.
Oh, so it's basically
All right,
the
so it
same
ends up
thing.
being the same thing.
Ah, okay.
So I'm integrating all of this from 0 to 1. Isn't it interesting how it works out? It just kind of goes to prove that integration by parts is like an inverse product rule, which is, I think I showed you briefly how they derived it. So when I saw all this f prime g of x, f g prime of x, it made me think of the product rule. So but it works out just the same way. That's very interesting. I'm glad you thought just straight apart. So I think maybe that's a better way to work it. Okay, so anyway, we'll do a couple, 2 or 3 every day, sometimes more if you don't have so much to do. All right, I think you have part of these handouts already for our topic for today.
I think we have all of them.
Yeah, I have a lot of pieces.
But I did
so
it
many.
again, just to make sure, because I didn't want to get up here and like,
No.
everybody looked for stuff. Our time is of such great value right now that I just ran off a bunch of stuff for you. So I tell you what, let's just start fresh with this. I apologize to Joyce, because I'm a big recycler also, but I also care a lot about the AP examiner time.
We'll
Yeah,
recycle
who
it
knows if
after.
we'll
I mean, I
have
am
another-
too.
Who knows if we'll have another snow day?
Not at this
Oh my
point.
god, could you imagine? I would cry.
Okay, you
But I'd
should
be
have
happy.
parametric equations, vectors, and calculus. And then it should end with answers to worksheet 3 on vectors.
Mhm.
Is that correct?
Yeah.
Only, I hope I ran it off. Answers to worksheet 3. Does worksheet 3 only have 7 questions? Yeah. Okay, that works out.
I already asked him if he has a.
Okay, so,
Oh, I'm gonna need another fiber for this class.
Yeah, same.
you might need one to like end the year with.
Yeah.
We'll see.
Yes, my math. I have the accordion code, but like the math one is bulging and
Yeah.
everything else.
You should see my art history binder. All of my notes are larger than a 3.
I have a
Okay,
separate history binder.
I had told you before the break, if you're asked for dy over dx, and you have what's called parametric mode, where your x and your y are changing simultaneously, like you did on the parametric worksheet 3 weeks ago, okay? So if you want to find dy over dx, really watch the writing. If you have x of t defined, and you have y of t defined, you could be asked for dx dt. You just take the derivative of that one in terms of t. You could find dy dt. You just watch your letters. But if they ask for dy dx, we've got to put dy dt over what?
Dx
dx dt. And if you multiply by the reciprocal, it becomes dy over dx. That's the first thing on this page here. Okay? If you're taking notes, maybe one reason I handed this out to you is because you might want to take notes on this. It's just up to you. But it's all right here. It may flow a little bit better. Or read it and star it, or take your own notes, whichever. All right, now the second derivative, I think all of you girls were here the day that I did the second derivative. We were all looking forward to spring break, so may not pay great attention. But if all I do is take the derivative of this, you're really not going to get the second derivative, because all that really does is incorporate what's just happened with y. So every derivative that you take, you have to divide by this dx dt. I don't know if you remember me telling you that. That's the tricky part about parametric mode. It's not hard. You just got to remember, every time you take a derivative, you're going to take the derivative of this. I guess I'll write it like they did in the book. I was going to put a little prime up there. I guess I still will. You're going to take the derivative of that, but you've got to divide it by dx dt. Because when you do this part, when we actually work a problem, it's kind of weird. Dy over dx will have a t in it. Okay? We'll take dy dt over dx dt, and so it'll still have a t in it, but since we divided it, we also know that it's still the derivative. But then if we take the derivative of that, technically all we will have done is have a dy dt right there. And you've got to incorporate that. You need another dy dt over dx dt, so the letters really get a little bothersome, but we'll do some just to tone it down, okay? But in parametric mode, you have to continue to divide by that. If I wanted the third derivative, okay, which I don't know why I would, but if I did, I would take this derivative of this and divide it by what? dx over dt every time in parametric mode. It doesn't come up a lot, but if it does, you don't want to miss it, because I'll have that extra step in there. We'll do something. All right, now, reading down your sheet, x prime is the rate at which the x-coordinate is changing. It's dx dt, and y prime, if they just write it like that, is denoted dy dt. I told you about vectors a little bit. Vectors, they have a magnitude and a direction, okay? And so our picture of the day really should be vector from Despicable Me, but I need to keep moving. I'll get all lost on this one of my favorite movies. But anyway, the position vector is x, y. The velocity vector is a dream come true. You just take the derivative of x and the derivative of y. You don't have to worry about a dx dt if it's spread out already as a vector. You can keep it all in terms of t. And the acceleration vector is just a derivative of the velocity vector. Real easy things to do on the AP exam, you just gotta be told what you're allowed to do. We'll make sense of it all. A dy over dx, of course, is always the change of y with respect to x, the slope of the tangent line. And the second derivative is the rate of change of the slope of the curve, acceleration. Okay, now, what you would like to have known is at the bottom here. The speed of the particle is the magnitude of the vector. Okay, now I don't know if that makes sense to you right now, but if you think about, we're just going to make a little bit of sense of it so that we can keep on moving. Because there's not a whole lot of parametric or polar on the exam, but there's enough of it to where we want to keep getting problems right. They're usually pretty easy problems. Speed, if I told you that the velocity was 40 miles an hour, or if I told you the velocity was negative 40 miles an hour, what would be the speed of the particle would be 40, right? Okay, so it's the absolute value of velocity I think you mentioned earlier. You probably talked about it with your other teachers also, but what have we talked about when we've said things like, what's the square root of x squared? It's the absolute value of x. Y'all all remember that? Okay, so if I really want the speed of something with x and y components, I get the speed of the particle by taking dx over dt squared plus dy over dt squared. And to try to make a little bit of a sense of it before we move on, if you think about what that is, that's the velocity squared, that's the velocity squared. You square root it, it's sort of going back to the absolute value of velocity, which is speed. So I guess I'm kind of a little nervous to write this up here. This isn't going to be velocity, it's going to be the absolute value of velocity, which we've defined for a while as speed. Okay, but if your components are separate, that's how you do it. Another thing, this will help you, I think, a lot, depending on how much your individual pre-AP, I used to call it pre-AP pre-calculus, your honors pre-calculus, I don't know how much you study vectors in there, so in parametric mode. But a vector in physics, okay, has a length and a magnitude. The length of it tells you its strength or its force or basically how fast it's going. When I've done vectors, when I teach pre-calculus and I do two airplanes that are going at certain, or a wind's blowing on an airplane. If the wind's 30 miles an hour and the airplane's going 300 miles an hour, I certainly signify that by the length of the vector. Is that okay with everybody?
Mm-hmm.
Is that okay? All right. And so doesn't this give me the length of the vector? So it gives me the speed of the vector? How long a vector is tells you how strong a vector is. So hopefully that makes some sense. So you just go in there knowing if they ask me for speed, I'll do that. Okay, and then we've covered the last thing on the sheet, the length of the curve. If it's in parametric mode, you don't have to do the 1 plus the derivative squared. You can just, and really and truly, it's very interesting. Isn't it very much like speed?
Oh wait, but that's just, I remember that from physics, that's just, because I was thinking, wait, but wouldn't you have two vectors, but it's just, you're literally doing.
Yeah, your x component and your y
the-
component,
yeah.
so it gives you this.
Gotcha.
Okay, and then, do you see how this transforms easily into the length of the curve? Because what you're doing is you've got little vector, 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 like that. Okay? So if you just want the speed, do this one. If you want the length of the curve, you're going to find those from A to B. All right, somebody had a hand up that I was ignoring. And it wasn't one of those, but I'll answer your question.
Well, I have a question. Is,
Comment?
well, no question. This is for like speed and distance, or like absolute value. Sometimes, like position and displacement are just different. And so like speed, like this makes sense for speed, like the velocity when you have them, or for position. I was just wondering how you do that.
We don't have to do it a whole lot. We do it some, but we're more interested in things are moving to the left and the right, as opposed to what I'm talking about right now. Like just the speed of the vector would be the length of the vector or its magnitude. We will look at somewhere like what direction is it going in? Is it moving toward the origin? And I don't know if I'm answering your question. We do look at the direction of the vector also, but that's just not what I'm talking about right now.
I mean, like if you wanted to do
I don't know, I feel like distance and like displacement and like position are just different.
Oh, I
things.
get what you mean. Great question. And that's gonna come up today, later on. Very good. I'm so glad that you're asking that. One thing that, what Lola's mentioning is I've gotta be really careful if I'm trying to find the total distance traveled, if it's not always positive. If it's always positive, I can just go from A to B. If it's not always positive, I'm gonna get the wrong answer. If this is 2 and this is 3, it's gonna tell me the distance it traveled was -1, okay, if I just add it up. But the distance it traveled obviously is 5, right? Okay, so again, we'll delve into all of that,
Is
okay?
it like how you can do like the
Well, I've got a few problems today that we'll get to, and I'll clean them up. All right? Another question?
No, I was just saying, is this like how when you take the, if I took the NFL that to try and find the area, like I wouldn't get the area because there's a negative.
Right. So you've got it. Don't ever find area or total distance traveled without looking at a picture first or considering if it turned across 0 or whatever you want to say. So don't be tricked by that, okay? If you're asked to find area from 7 to 10, you better check and see what that thing looks like from 7 to 10. Or total distance traveled from 7 to 10. At 7, it could be a 4. At 10, it could be a 4. You could go, well, it didn't go anywhere. That could be very untrue, right? So we always check our velocity. We always want to look for turns, okay? Now, Lola, it's not too much of a problem in vectors, though, because of all of that's going to be positive. Like the way around it, we'll work some problems. I'll show it to you easier that way. Okay.
Because I was just saying, like, if there's like, you couldn't do this. Or you can't just make them positive. Like, you have to account for the fact that they're negative.
But we will. Okay. All right. Now, look at worksheet on parametrics and calculus. Is that your next page?
Yeah.
Worksheet on parametrics and calculus. All right. Let's do number 3. We're not going to do all of this. We'll just kind of spot and make sure. Saving paper. While I'm not saving paper. Okay. All right, notice the directions say find dy over dx. Okay, everybody see worksheet on parametrics and calculus. And you have the answers to it also, depending, the reason I provided all of this to you is because as fast as I've moved all year, really, I know that you might all of a sudden get curious about, wait, I didn't really quite get that. It gives you some more to practice and you can check your answers, okay? I have a test tentatively scheduled for sometime in class, but there's a high chance that will turn into a take-home test. At most, you would have 2 more tests for me if we get that in. It may just be 1. But I'll keep you, we'll talk about it more on Wednesday. Okay?
That would be lovely.
Good.
So weird.
Yeah.
As we have 4 weeks left.
Okay. Now, to find dy, yeah, I do too, but even though you probably just got some dirty looks. All right, dy over dx, I'm going to take dy dt, which is 6t plus 2, over dx dt, which is 1/2 t to the negative 1/2. So if we're going to do a spotty few of these, I want to go slow enough for you to keep up. All right, let's bump the 1/2 up there first. Instead of dividing by 1/2.
Why is it negative?
Oh, dx dt?
Yeah. Why is the dx?
1/2 because you bring it down
And subtract 1.
Oh, I'm sorry. Okay, I was not doing that in my brain.
Bring that back over.
Let's bring it all back up. Yeah. So first thing I'm going to do is instead of dividing by 1/2, I'm going to multiply by 2. That's going to be a 12 and a 20 and a 4. We're at 12 and a 4. And we're at 24. And then the t to the negative 1/2. Stephanie, we're going to put that up there. We have t to the first, and t to the 1/2 is t to the 3/2, and 4t to the 1/2. I mean, do it in steps if you're, you don't want to miss something easy like this. A whole lot of why I have to do parametric with you is just so you know what you're allowed to do. At the lingo, you know what you're looking at. It's really not very difficult. All right, now the second derivative. All right, so here's what I was trying to tell you earlier. Do you see if I just take the derivative of that, it's really just a dy dt? I've not incorporated the x into it at all. Right now, this is a dy over dx, but it's in terms of t. I can show you later how all this works, or why it works. Right now, we're just going to do it. When I bring down my 3/2, take the derivative, what's that give me? 18? Yeah, 18t to the 1/2 plus 2t to the negative 1/2, but I've got to put that over dx dt, which was 1/2 t to the negative 1/2. So to find the second derivative is that little trick where you go on and take the derivative of this, but every derivative has got to be over dx dt. All right, we'll clean this one up. So we'll multiply both of those by 2. All right, so this is going to be 36 and 4. And then this is going to be t and nothing, right? They'll cancel at this point right here. So that's my second derivative. And I guess I'll just say it to you. And right now you have to believe me until I have a chance to show it to you. Back 3 weeks ago when I gave you that worksheet on parametrics that you were supposedly maybe hopefully learn some of it in the pre-cal course. It's hard to get to in the pre-cal course. There's a way to write this as a function of y in terms of x. If I solve this one for t and sub it in here and take the derivative, okay, and I check them against each other, let me see if I'm saying it right. I guess I might as well do
No,
it.
that was right.
And I think I'm just going to say too much to like wrap my own head around it. Okay, so let's make it easy. Let's say x is equal to t over 2 and y is equal to t squared plus 1. All right, now I ask you for dy over dx. All right, you have two options really. I would do option 1 that I'm teaching you today, 2t over 1/2 4t. Is that okay? Have I made a mistake really? But you also understand it? Okay. Option 2 though would have been to just write it as y in terms of x as an old-timey function, okay? And just take the derivative. So let's try that in another color. All right, so 2x is equal to t, right? And so y is equal to t squared plus 1. I think this is better oriented. And I'm going to put in 2x. So y is equal to 4x squared plus 1. What is dy over dx equal to? 8x. All right, but what was x? Do you see those are the same expression? Everybody see that? Okay.
Oh, that's 4.
Sorry.
Yes.
Yeah,
I can
dx, right? Underneath the d. Is that
Oh, thank you. So I think that's dy over dx.
Yeah.
Okay. Now the second derivative should come up being 8, shouldn't it? It should be 8 in the end. All right, now let's take the second derivative of this one. If we keep it, so do you see your options are, do you want to keep it in parametric mode or do you want to do it in function mode if they start asking me these questions? Okay, I want to do it in parametric mode, but I want you to see what you're doing is right. All right, so let's take the derivative of this, which is what? We would have just gotten 4, wouldn't we, girls? We would have missed it. And if the answer's not 4, the answer's got to be 8. We can see it from our old function mode. We always have to divide it by dx dt, which is 1/2. So that's what I was going to try to say to you. Is everybody okay with that? Okay. You got to kind of explore around it in a little bit to see it, and that's as much time as we have to explore. So let's move on. Oh, this was dx dt. Sorry, that was dy dt, and this was dx dt.
Gotcha.
And my point here was, why do you keep dividing by dx dt? And so I just used some simple. You can go back and forth from function to parametric mode. Okay, and they'll ask you to sometimes. All right, let's do, where's my page? Okay, let's do a trig one. Or no, let's do a logarithm one. Let's do number 4. I just deleted the page. They didn't orient it that well. Okay. All right, number 4. So I have x is equal to ln t, and y is equal to t squared plus 1. All right, I'm going to write myself a note. I'm going to need dx dt, maybe over and over again, right? I've got to put this underneath each derivative. Again, this stuff's pretty easy, but if you're asked for dy over dx, I'm afraid some people would just come up to this and say 2t, right? But dy over dx is dy dt over dx dt. You got to know they're going to have just that also in the multiple choice though. So this is 2t squared. Check my answers. Make sure I'm not doing myself. What am I doing, number 4?
Yeah.
Oh, I did mess up.
dx?
I must have copied something down wrong. This is t squared plus t. Sorry.
Yeah.
T squared plus t, which made this
Plus 1.
plus 1
So 2t squared plus 2.
to 2t squared plus t. All right. And then the second derivative.
Sorry. is it
Oh, I
dy
did it
dx?
again, didn't I?
Oh,
Yeah, I was so
I did it
Very
again.
sad.
I'm sorry. This is dy over dx. If it had said dy over dt, I would have been. If it had said dy over dt, I would have been done with
Yeah,
2t plus 1. Okay. So the second derivative, if you can read the first derivative, is 4t plus 1 over what?
1 over 2.
1 over t. And so you get 4t squared plus t.
Is this? Oh, it's a water. It's never gonna like simplify in polynomial, right?
Say it again.
Like, there's a lot of it that's hard to simplify in polynomial. And always that's where.
Oh, yeah, that's interesting. I hadn't thought about that, Lola. How interesting.
Yeah, because you're always
Yeah.
going to divide by 1 over 2.
And the logarithm also that doesn't go away. Is that kind of what you're saying? Probably, yeah. It would happen with I would expect it to happen with an exponential function.
No.
Because I
Oh, we're
took
taking the derivative. Okay, now I'm getting myself confused.
Yeah, that's because of me. All right, let's skip number 5 and go on to number 7, because that way I'll capture a trig function as we go. All right, so this is number 7. All right, number 7, a curve is defined by x is equal to 2 cosine t, and y is equal to 3 sine t. All right, and we've got to watch for if they were going to ask for dy dt, dx dt, dy dx. All right, on the a part, they asked for dy over dx in terms of what? T. All right, which is good news. I like that. Dy dt is 3 cosine t, and dx dt is negative 2 sine t. If it's a free response, you're free to leave it like that. Multiple choice, you'd probably see it as a cotangent. Right? This one would be a little bit unfortunate if they asked me to find dy over dx in terms of x, because I'd have to get into inverse trig functions and little triangles with square roots and stuff. So I shouldn't even brought it up with this one. But you've seen one before where you can get it in terms of x. If you want to solve one for t and sub it into the other one, you could do all of this in terms of x. All right, and then find an equation for the tangent line at the point where t is pi over 4. All right, I want to make sure I got over one of these.
Can you write a parametric?
Well, sometimes.
No,
It's in comparison. Yeah.
good question. You're still going to need y minus y equals m times x minus x. You are now writing the equation of a line. Parametric mode, what it does is it adapts for the fact that the point's changing simultaneously. But right now, I actually need an equation of a line in terms of x and y. But I can find x and y when t is pi over 4, right?
Mhm.
All right, so when t is pi over 4, cosine of pi over 4 is square root of 2 over 2, so I get 2 square root of 2 over 2. the sine of pi over 4 is square root of 2 over 2, so I'll get 3 square root of 2 over 2 right here. So it's real ugly. I get y minus y, x minus x, and now I need the slope. And you've got a few choices here. You could fill it into this, or you could fill it into this. You could go back and find dy over dx in terms of x, which I wouldn't do. But what is it, first of all? Right now I need a t or an x. A t. All right, my first derivative, my slope of my tangent line right now is still in terms of time, so that's okay. When I fill in pi over 4, thank goodness that's just 1. Tangent of pi over 4 and its reciprocal cotangent's 1. So my slope is negative 3/2. On free response, we can just leave it like that.
Wait.
Okay.
I target cosine of pi over 4 to be 2. I mean 1.
Oh, that's cotangent. I filled it in this one, which was a good reason to go on with my identity, because it would have been a little bit tougher right there. Well, not really though. If you had gotten square root of 2 over 2 over square root of 2 over 2, it would have canceled out. If you'd have left it like that. Okay, now let's go to, let's stay with some trig. Let's go to number 10. All right, number 10. Find dy over dx in terms of t. All right, so number 10. All right, I have x is equal to 3 plus 2 cosine t, and y is equal to negative 1 plus 4 sine t. Make something really interesting. I don't know what it would make. All right, now, remember with things like this, you can make like ellipses and circles and hyperbolas and stuff. I would expect this to be some sort of ellipse. So dy over dx. All right, so the derivative of that is 4 cosine t. And the derivative of dx dt is negative 2 sine t. So I'm going to get negative 2 cotangent t.
Can you leave it
You can, go ahead.
for like cosine or sine for free response?
You sure can. In fact, if you look at the answers, they left it like this one right here. Okay. Now, in fact, I'm really going to want this a little bit more than that, Lola. I can work with this and what I'm about to do, but this is a whole lot more helpful for the rest of the question, because they ask you for find the points. Where's the question? Points. Now, first of all, underline the word point. They want an x and a y. They don't want a t. They want the point. You can't see time. They want the point where this. And so remember how when you did parametric mode, we had some that did stuff like this? Sorry, it's not very oriented. I don't have a pen. But y'all know what I'm trying to draw? Like it might go around like this. And you would draw your arrow of direction. Okay, so do you see how it could have some horizontal and vertical tangents? All right, where do you have a horizontal tangent?
Is this in terms of x and y that we're talking
We'll get there, but we've just got to figure out right now, very literally, how would you have a horizontal tangent? Your slope would be 0. What would make this slope 0 is if 4 cosine t is equal to 0 as long as sine is not 0. You can't have 0 over 0. Okay? So if, Grace, if my derivative, we'll get to x and y eventually. If my derivative is 0, it'll happen when 4 cosine t is 0. And I'll double check it in the bottom. All right, when will cosine equal 0? Do we have a range here?
Pi over, oh, I don't think so.
No.
Pi over 2 is like plus pi.
We'll just do it with pi over 2 and negative pi over 2. Let's see, where are the answers? No. That would normally give you a domain. In fact, I'm gonna go from 0 to 2 pi because that would be a little more typical, not always. We'll do one later that doesn't. Let's just go around pi over 2, 3 pi over 2, around one cycle. All right, now the bottom is not 0 then, is it? So we're safe. We've got 0 over a number, which gives us a horizontal tangent. Now, Grace, what you were asking is these are just now t's right now. I don't have a point yet. Let's just leave it for just a second, let you think about it. All right, now we can actually find the point, and if it's a free response, we need to write what we're saying to find the horizontal tangent. At t equals pi over 2. I'm going to go back and say x is equal to,
3 plus 2 plus 2.
thanks, I've lost all my pages, 3 plus
2.
2 cosine of pi over 2. What is x at that moment that you have pi over 2?
3.
3. All right, now Lola said pi over 2 and negative pi over 2. I kind of changed it to pi over 2, 3 pi over 2 for one rotation. But once I get to this, we realize it kind of doesn't matter that they didn't give us a range, does it? Because every time cosine is 0, I'm going to get 3, whether I fill in 3 pi over 2, negative pi over 2. Every time I hit that, that's going to go away. And so it's going to happen when x is 3, okay? All right, and then I can find my y-coordinate the same way. So do you see how I found a time, and I fill it in to find my x and y-coordinate? My y-coordinate was what?
Negative 1 plus 4 sine.
What's the sine of pi over 2?
1.
And so what do I get?
3.
I think I get 3.
3.
All right, so 1 point is 3, 3. But I have an issue here now. What happens if I fill in 3 pi over 2 or negative pi over 2?
You had a different
Oh,
answer, negative 3.
Or I could have negative 1 plus 4 times the sine of 3 pi over 2. You could also get a y of
No, wait,
negative 5. So it's a situation like this, girls, and this little picture that I drew, because I think this one will be elliptical, it could happen at 3, 3, and it could also happen at 3, negative 5. Do y'all see what I mean? Now, did we take care of, like what I said, I didn't know how many cycles to go through, but it doesn't matter, does it? It could either be 1 or it could be negative 1 in terms of sign. All right, so that's how you find the point. If you've got your time, you can find your x and y coordinates. All right, now, vertical tangent. Let's do vertical tangent. So vertical tangent is when the bottom's 0 as long as the top's not 0. So on our free response, we'll let them know what we're working on. Now we're working on vertical tangent. You don't have to go overboard. You'll just let them know that you're saying when the bottom is 0. What's the bottom?
Negative 2 sine 2.
All right, negative 2 sine t. When is that equal to 0? At t equals 0, pi, 2 pi, and so on, right? We realize we got to think probably of what happens at 0 and at pi. All right, now they said the word point. I had you underline that, so you've got to go back. A lot of kids would maybe stop. A lot of students would stop at the time, but they want the point. Now, watch it, girls, because they may say, at what time does it have a vertical tangent? And you just leave the t in there, okay? X is 3 plus 2 cosine. Let's start with 0. All right, what's the cosine of 0? 1. So this gives me 5. All right, I better do the other one then, right? Because I got a 1, so I'm thinking I also could get a negative 1. Or I could have 3 plus 2 cosine of pi, and I believe that will give me 1, won't it?
Negative 1?
No.
1, yeah, 1. Yeah, 1.
3 minus 2.
Cosine of pi
Is negative 1.
is negative 1.
So 3 minus 2.
Oh, of the whole thing.
Yeah.
It's like,
All right, and my y is negative 1 plus 4 sine, is that right, of 0.
Yes.
And what's the sine of 0?
0.
So you just get negative 1. And could anything else happen there? Good. All right, because Grace, if we had, I'm sorry,
0.
Joyce, if we had 0 or if we had pi, This part's gonna be 0 no matter what, right? In our scenario. So what are those points? Vertical tangents occur at 5, 1, and at what? 5, -1? Oh, no, that's wrong.
-1.
Sorry. 1, -1. I better rewrite the whole thing. I'm messing this up. At 5, -1, and at 1, -1. All right, looking back at my picture, given what we studied about parametric mode, do y'all see that can happen? Do y'all see that, girls? If it was oriented, I could have those two vertical tangents, one out here and one back here, as it moves along the axis.
So they would have to give you like a domain.
No, in this problem, they didn't have to give us a domain because it just goes around and around forever like this. Do you see how we talked about at 0? I'm sorry, let's go back to your pi over 2, okay? At pi over 2 something may be specific. At pi over 2, the x-coordinate was 3, okay? So I knew you got it? Okay. Do y'all see this is just an A and a B part? What I really foresee here is there'd be a third part. The first part would be the graph with the direction arrow. And then the mastery maybe for the derivative and then vertical and horizontal tangents. If it was really a free response. All right, now let's go to the end. Y'all try 11 and 12 real quickly. Based on what we talked about today. I tell you what, just do 11. So we can move on for 5 minutes. Did I say just do 11? I meant just do 12, but you probably already started on 11. That's okay. Just do 11. What's our formula we're using?
Integral
Like the R. Integral
Yeah.
of the square root of dy dt squared plus dx.
Yes.
That was way too hard to say.
Did everybody get this right here?
Oh, I mixed up 11 and 12. Should we
Wait,
simplify
I did
that?
the other day.
Should we simplify the
Did
square?
I mix up 11 and 12?
No, you didn't.
Okay.
Should we simplify the square?
Yeah, I'd go in and call that 4t squared and 9t to the 4th.
Okay.
If it's a free response, you could just leave it then. Now, it's interesting that they just said set it up
Right.
because you couldn't integrate that. That'd be really difficult to find the antiderivative on. This would probably be one you just either punch in your calculator or leave it alone.
just distribute the 1/2 exponent.
No, you can't do that. The square root of x squared plus y squared is not equal to x plus y.
I mean, if you multiply them, it will make
No, but you'll end up with x plus
There's
y.
no anti
Yeah.
and touching.
Right, that'd be a very difficult integral to take, unless you were lucky enough for something to come out of the square root and maybe substitution might would work,
Wait, actually,
but it'd be highly unusual.
why can't you multiply by 1/2 and then just use it then?
Multiply what by 1/2?
Like if you had like 2, like so it ends up being 4t squared plus 9t to the 4th, and then you like multiply those exponents by 1/2.
That's what we're saying you can't do, because that's what I was like,
But why can't you do it?
because of that. It's just Those aren't the same.
If you have
No,
x
when you have-
squared plus y squared to the 1/2 power, you're still stuck. You can't call that x plus y. Because of order of operation, you have to know what that is
You can't
first.
distribute that to me.
Is that what you were saying?
It goes back to when we learned how to do a quadrant.
Yeah.
Where's
Okay. Now, just real quickly for the last probably 3 minutes, 2 minutes, go to worksheet motion along the line. Okay, A. How do you think you're gonna find when the A, number 1. And the answer is I don't think is A. All right, how do you think you're gonna find out when the particle is at rest? X of t is 2t cubed minus 21t squared plus 72t minus 53. At what time t is the particle at rest? Now, particles moving along the x-axis, this one's interesting. It doesn't even have a y component. If it's moving, if you've seen the one time I turned my calculator in parametric mode and watched it like move around, this thing's just moving like this back and forth along the x-axis, left, right, left. So my y component right now is 0. All right, so the question is, when is it going to stop? When its velocity is 0. So I'm going to find dx dt, which is 6t squared minus 42t plus 72. I'm going to factor out a 6. That gives me t squared minus 7t plus something, 12. So I'm going to set that equal to 0. When I factor t minus 3, t minus 4. And so what happens when you have 3 seconds or 4 seconds? And so I guess the answer choice is E. For later on, because I need to stop, I need to wrap it up. For later on, if I give you a problem for homework that you have to do what I'm about to say to it. If you have a y component, they both have to be at rest. The y component cannot be also moving. Like, it can't be moving vertically. It's got to be stopped vertically and horizontally.
So do you have
So let's say if I had a y component too, and it was at rest at t equals 3 and t equals 1.
You only take
It's only
the
at 2
three.
equals 3, okay? And if it doesn't have anything that matches, the thing's never at rest. But I've never seen them ask you that.
That's like an interesting problem for acceleration. Was like that actually happened with acceleration.
If there was a y component.
You mean like when both components are?
No, like an acceleration, like actually, like one component can be 0.
Yes.
How do you know
Yeah.
it's 3?
Question,
Yeah.
how do you,
Where
could
X
you
is
just,
also at
if
rest.
that's the
But
case, if
one
you also
more.
have a y component, could you just find the derivative in terms of x and y, and not in terms of?
That would all play together if you did it. Like that time I just stopped and did a slide and interchanged them. It's just that this was so hard to solve for t and impossible to solve for t. You couldn't go that route with this one. Okay? But Grace, if you did, if you were able to get it into terms of y in terms of x, and you took dy over dx, you would find out, now this is what's interesting. This happens when t is 3 and when t is 4. We don't know what the x is at those moments. It all would mash together.
In that, yeah.
But
Well, what do you do then if you're what was the thing you said, if one is moving and one isn't, you have to?
if you have a y component, this one doesn't have a y component. It's just moving along the
Yeah.
axis. But if it's moving around like that last one you did, it's got to be completely stopped. That means the dx dt and the dy dt both have to be 0.
So you'd have to do the same thing for this one and find the t's and compare the t's and whichever one is for the, okay,
For
that's
dy.
good.
Okay,
That's-
homework. Let's just say you're going to finish